Hey everyone, in this video we're going to be looking at how do we solve linear equations using graphing. Now linear equations can be solved algebraically and you should have seen that before, but we're also going to look in this one about how to do the same thing using a graphing strategy. So looking at this problem that's in front of us, we have this question about which resort membership is best. If we have two options for this, maybe a beach resort, the first option A tells us that it's $1,500 to join this club membership, and then after that, or in addition to that, it costs $75 per year. So we would have to do $1,500 initially to join, and then have to pay $75 per year. In option B, we would have to pay $1,900 to join, and then pay $50 per year. So if we're asked the question, which resort membership is best, then that's a little bit of a tricky question to answer, because we have to determine, well, what really defines being the best? I mean, how do we determine that? In this case, based off of money and knowing nothing else, we would say, well, the membership that's best is the one that's going to cost us the least. So we would need to know which one would cost the least. Now, obviously, if you look at this, initially you may say option A is better because it costs $1,500 up front versus the $1,900 up front for option B. But if we go with option A, notice that it's going to cost us per year more. So this one, it's a little bit less obvious to answer this question, which membership is best. And this is why sometimes it's good to be able to graph a situation, because when we graph, we're able to see the relationship that's going on between the two scenarios and compare those over time versus looking at just one instance. So let's see if we can actually write an equation for each one of these to model these. And these each would be linear equations because they have a constant rate of change. So in both instances, it's going to be the same year after year, which is the definition for being linear, a constant rate of change. It never changes how much it goes up by from year to year. So for option A, if we look at that, remember our linear equations always have this format of y equals mx plus b, where the m is the slope or rate of change and the b is the y-intercept, or the starting value. That's another way of thinking about it. So in this situation for option A, our equation to model this would be y equals our m as our slope or our rate of change would be 75x plus 1,500, where x is how many years we have it and y would be my total cost. For option 2 or option B, it would be y equals 50x plus 1,900. Now that we have our two equations, we can actually go to a graphing utility, whether that be a calculator or Desmos, and actually see what this looks like visually. So let me grab that so we can see these. Okay, so looking at the graph that here in Desmos, you can see our two equations. The red line is my option A, where it has a lower starting value. So there you can see there's that $1,500 is my starting point where we are joining, and then we're going up by $75 a month, and then the blue line is where we're starting at $1,900 and going up by $50 a month. So if you look at this, remember our question is which one is best, and we determined that being best is done by looking at which one costs the least. Looking at this, costing the least depends on where you're at. If you are in the lower area, down in this region, then it looks like option A would be the cheaper option. However, we reach a point to where the two lines are equal, where they intersect. At that point, it really doesn't make a difference which option we pick. They're both costing the same thing. And if we touch that, we should be able to see what that point is. So you can see after x being 16, and remember x was years, so after 16 years, they're both going to cost us $2,700. If I go beyond that, however, option A becomes more expensive. You see how that is higher. And then option B is the cheaper option. So it really depends on how long we want to be in this gym membership, or how long we anticipate being in the gym membership. So as you can see, looking at the graph, there's a lot of different questions we can answer. One of those being, how do we find the intersection? Of course, we see that here on the graph with Desmos, makes that really easy, and that represents the point where both equations are the same. If I want to know which one is the cheaper option, then we can see it changes based off of which side we are on that 16-year mark. So if I come back to our question, which resort membership is best, one way I could answer this is I could say that option A is best if we want to keep it less than 16 years, or I could say if X is less than 16, because remember X was my year. I could say option B is best if X is greater than 16. Now notice I did not include equal to here because when X is equal to 16, they are both the same, option A and option B. Now let's suppose we started this same problem out the same way that we did initially, but I'm going to change the question a little bit. What if my question this time was instead, when is option A the best? Now, obviously, we already know that answer, so let's approach this like we do not know the answer. So in this situation, representing it mathematically, I have my two equations, but what I'm asking for is when, sorry, okay, my apologies for that. So again, the question is, when is option A the best? And you can see we have our two equations here. So when answering this question, when is option A the best, if we turn that into math for us so that we can actually work with that, then I want to know when is the first option less than the second option. So if we write that using inequalities, I can write it as, whoa, do not know what happened there. Let's take that back out. Let's try this one more time. Okay. So it would be, when is 75x plus 1500 less than 50x plus 1900? Now, there's different ways we can do this. One way is we can solve it algebraically, which I am going to go through this algebraically, but I'm also going to do it graphically so you can see how both options work together. So when is option A the best? Meaning when is option A less? And that's why we have put option A over here on the left being less than option B. So to solve this, we will just simply solve for x like we would with any equation. So we need to get all the x's on one side. I'm going to subtract this 50x over here, which would make that go away here. 75x minus 50x would be 25x, bringing down the 1500, copying my inequality and bringing down the 1900. So we're trying to get x by itself, so I'm now going to subtract 1500 from both sides, leaving me with 25x is less than 1900 minus 1500 is 400. And then if we divide that by 25, we should get that x is less than 16, which should make sense because remember a while ago we learned that 16 was that changing point. And we said that anything less than 16, option A was better. So you can see how this was showing up here and how it was working for us. All right, so we can still do this same thing with Desmos. So let me grab that real quick. And let's look at this from a slightly different perspective. So what happens if I actually type this in the way we were doing before? So I've come back to Desmos and you can see we still have my two original equations in. And if I want to know when the 75x plus 1500, which was option A, was less, well, you can see that here. It's lower in this area. So this is where the graph becomes really useful. And that starts being lower, or it stays lower up until we reach this point of 16. Now, if I come here and put in this equation or this inequality, like we were just solving, and activate it, look at what happens. It shows me that my solutions are all of the x values to the left, shown by the shading, left of 16, which again was our answer. Anything less than, let me get this out of the way, less than 16. So there you go. There's how we solve this question looking at it from that point of view using inequalities. Now, before we wrap up this video, there's one last thing I do want to show you, and that is how do we look at this last piece referred to as, now that, zeros of a function. Now, one way to think about this is when you talk about the zero of a function, what you're looking at is what would make a function equal to 0. So let's suppose we have this function negative 2x plus 8. So whenever we're talking about zeros of a function, we're actually talking about what would make this function equal to 0. So in other words, I'm looking at, hey, what would make negative 2x plus 8 equals 0. Now you can look, and sometimes you can just spot this immediately. Other times you need a system to go through this. Well, when you set it equal to 0, you're essentially just solving for x. And if we do that by subtracting 8 from both sides, of course the 8's would remove themselves because they're opposites, and then we would have negative 2x is equal to negative 8, where we could then divide by negative 2 and get that x would be equal to a positive 4. So x equals 4 would be considered a 0 of this function. Now, another way we could look at it is looking at it graphically. So let's look at what happens at a graph, and this is a little bit interesting. So if you look at this graph, and we're talking about zeros, well, we just found out that x equals 4. Well, look what happens when x equals 4. That's here. And notice that when x is 4 on this function or on this graph, the y value is 0. And that's because when we use that x input of 4, it makes the function become 0, which is why it's referred to as the 0 of a function. So a short way of thinking about this is that anytime we're talking about zeros of a function, you could talk about the zeros as the x-intercepts. And you're really talking about almost the exact same thing. You could also refer to it as the solutions to a function. Almost the same thing. There's a little bit of difference here, but we'll get into that a little bit later in the course. But these three things are really closely linked together: zeros, x-intercepts, and solutions. Okay, so that's our discussion on solving linear equations, how to use the graph to solve those linear equations, also bringing in those inequalities for some situations, and then also looking at zeros of a function. Take care.